Today we're going to look at inelastic collisions. Now for a collision like that, we really don't expect the truck to lose too much momentum. So let's consider a collision of two objects of comparable mass. Let's collide this here 1 kilogram wad of chewing gum with this 2 kilogram block. Now if you made it this far, you're definitely a physics student, so I want to help you out. We're going to be doing some problems. You want to pause it before you see my work, see if you can do it yourself. And then just press play and pause as you go through, see how much help you need. Alright, let's take a look at this problem, and we're going to use our standard problem-solving strategy steps. First step is to always read and understand what's happening and what's being asked in the problem. Identifying the question just looks like the variable with a question mark, so VF in this case. Next step, we're going to apply the law of conservation of momentum, and that looks like this. PI equals PF. Next step, we're going to identify anything that has momentum. So before the collision, two separate masses, M1V1 and M2V2. After the collision, M1 and M2 were stuck together, so we're going to group them with parentheses here. Now M2 wasn't moving initially, so we're going to cross that out. And then the last step, really, you're just solving for the unknown, in this case VF. So we're going to divide both sides by the sum of M1 and M2. And that's going to give us an expression for VF. And at this point we can plug in our values. I think that's 1/3 times 2 meters per second. So that should be 2/3 of a meter per second. Oh no. Oh no. Please don't. Please don't throw that marble into that block. Oh no. I won't even know what to do. Oftentimes, elastic collisions like these end up being both momentum problems and energy problems. So you're going to have to tackle things one thing at a time. So we've got two things we've got to worry about here. We've got a collision that happens between time 1 and time 2. We can do momentum work for that collision. And then we've got an upward swing between times 2 and times 3, and that can be done with energy strategies. If we're ultimately going to have to find out how high this thing swings upwards, we're going to need to know how fast it's going at time 2. Now, let's make that our momentum problem. So now that we've identified the problem, the next step is to apply the law of conservation of momentum. Set momentum before the collision equal to momentum after the collision. Next step, identify what kind of momentum you had before and after. So the marble had momentum before, and then afterwards, the marble and the block had momentum together. Finally, solve for V2, and you get this expression. Now the rest of it, after the collision's done, is just going to be a swing upwards. So that's going to be a transfer of energy. So we'll use our energy strategy, set initial energy equal to final energy. Then we're going to have to identify what we have initial and final. Looks like we're going to have translational kinetic energy turning into gravitational potential energy. I always like to put the external work term there just in case we have anything entering the system or exiting. And then we're going to plug in our formulas. 1/2 mv squared is going to be equal to mgh, and you're solving for h in this case. So we end up with v2 squared over 2g. Of course we would like to be done at this point, but you're not getting off the hook that easy, because you see this v2 over here? Well, we had an expression right there. So let's substitute that in for v2 and see what we get. Here we go. Boom. Sometimes it's hard to tell if they're asking you an energy problem or a momentum problem. So let's take a look at this particular question and try to determine what they're asking us. they're asking for force necessary to stop this bullet over a distance d. Now the variables they gave us was force, displacement, mass, and velocity. Now that could be tempting because we see m and v and we say, oh, it might be a momentum problem. But those make up work. Work is a transfer of energy. And we also have m and v in our kinetic energy formula. So let's use an energy strategy. Step 1, identify what they're asking. In this case, they're asking for force. Step 2, draw a picture. Well, that's done. Step 3, apply the law of conservation of energy. Initial energy equals final energy. Step 3, identify the forms of energy that are present. Now before the collision we had some kinetic energy, and then there was some work done on the system. Afterwards we have a bullet that's not moving, so we don't have any energy at the end. So our translational kinetic energy must be equal to the opposite of the work done on the bullet. That kind of makes sense. Next step, we apply the formulas. 1/2 mv squared is going to equal f times d cosine of theta. Now that theta is the angle between the force and the displacement, so our cosine in this case is going to be equal to 1 since they're collinear. And now you're going to just solve for f, because that's what we were set out to do. Looks like it's mv squared divided by 2d. And there it is in all its glory. Now that question could have easily been about momentum and impulse if we just changed one or two words. So now let's pretend we were given time interval instead of displacement. And you're trying to figure out, is it an energy problem, is it a momentum problem? The problem is still asking for force, and the other things you're given are time, mass, and velocity. So mass and velocity, those could be an indicator of momentum or energy. But force and time, those things, their product is impulse. So we can use our definition of impulse here. J equals F times T, which is also m times change in velocity. So solving for F, you're just going to divide by T, and you're going to get mvi over T, since the final velocity was 0. I'm Mr. H. I'm always solving physics problems. I hope it's contagious. Good luck out there.